Hello guys, welcome back to Mathematics Made Easy, and today we'll be considering stochastic integration by parts. Stochastic integration by parts is a technique used to integrate the products of two stochastic processes. Therefore, the derivation to derive this, starting from the stochastic product rule for differentials. Let's have a stochastic process S of t to be cross product of, let's say, S of t, G of W sub t. Let's say this is equation 1, where our f is a function belonging to this. It's a C1 function, which means that f is deterministic and was continuously differentiable in time. Yg belongs to C2 functions and this one is trying to tell us that it is twice continuously differentiable in the space. Though we should have it in mind that W sub t here represents the winner process, or you say Brownian motion. And one of the properties of a Brownian motion is that it is not differentiable. So it is not W sub t, which is a Brownian motion, that is differentiable, but this function. So it is this function that is differentiable. So this function serves as a smooth function for the Brownian motion, for the winner process. So it serves as a smooth function of the Brownian motion. Now, using the product rule, from 1, you can observe that the st now will be differentiate ft, keeping the second function constant, plus differentiate the second function, keeping ft constant. Now, let's try and expand this. So the ft is simply equals to f prime of t dt. Because we are having this join, so let's take it together. So that will be f prime j of w sub t dt plus ft. The definition of this is actually following the Taylor series theorem. However, in case of Taylor series, is to function of deterministic variable. But because this is involving a winner process, is to function of random variable. So it's still following that same approach. So the derivation of this follows this to be equal to g prime of w sub t the wt plus half g prime prime second derivative w sub t then the wt sub t all squared. So it is clearly stated earlier that g is what? Is twice differentiable, and that's why we have this. But take note of something here, that the w sub t squared is equal to the t, and this is actually coming from the knowledge of quadratic variation of the Brownian motion of the winner process. And this actually mirrors the what? The roughness of the path of the Brownian motion. So from there we were able to observe that the w sub t squared is equal to what? Is equal to the t. So having this result, let's put it back to our formula. So we're having it to be, instead of me writing the st now, I want to replace s sub t now with our product with this. So I'll be having the f t g of w sub t to be equal to, we're having that to be f prime sub t g of w sub t dt plus ft g prime of w sub t dt, sorry, wt, then plus half ft, so the ft will open the brackets, f sub t, then g prime prime of w sub t, and this one now has become dt. So this is the differential form. This is the differential form of the stochastic integration by parts. Now let's obtain the integral form. The integral form is obtained as follows. So we're still making use of this. So this is actually what the term we'll be using. We'll be integrating on through, but this is the term we'll be using as the subject, which is actually showing our integration by parts. So taking the integral from a limit, let's say from a to b, of f sub t g prime of w sub t, the wt, to be equal to this side now. Now if you integrate this, you see that the differential will cancel out the integration, and we'll be left with f sub t g of w sub t with the limit a to b minus, so we'll be taking this to the other side, taking the integral from a to b, f prime sub t g of w sub t dt, then minus integral, that will be half, from a to b, f sub t g prime prime of w sub t dt. So we can easily see that this term now is an extra term which is added due to the quadratic variation of the Brownian process, which does not actually exist in classical calculus. So the extra term minus half integral from a to b ft g prime prime this dt is due to quadratic variation of the Brownian process, which does not exist in the classical calculus. Now, this is the integral form of the stochastic integration by parts. This is the integral form. Though there are some special formula that we can master that will actually help us whenever we are solving questions that involve using stochastic integration by parts. And the first one is, if g of w sub t is equal to w sub t, then we need to find g prime of w sub t, and from here it will simply be 1, and g prime prime of w, the second derivative, this is the first derivative, which is 1, second derivative now will become 0, this will become 0. That implies that our formula now will become integral from a to b f sub t, our g of w is w, and the first derivative is 1, that would be 1. That will be left with the w substitute t to be equals to f substitute t, and this is given to wt now. Wt substitute t ranges from a to b, then minus integral from a to b f prime substitute t, g of wt is wt dt. Now we observe that this last term will become 0 because the second derivative here is 0. So it will not be involving the quadratic variation correction term. Another one is if we consider f of t to be equals to 1, then don't forget that f is once differentiable. So we only need to find f prime of t, which is simply be what? 0. And then realize that our formula now will become integral from a to b. Our f substitute now is 1, so we left with g prime of w substitute t, the w substitute t to be equals to our ft is 1, so we left with g of w substitute t ranging from a to b, the limit, then minus, we observe that f prime of t is equal to 0, so that shows this second term will be 0. So we left with this, which should be minus half integral ranging from a to b f substitute t, which is 1. So we left with g prime prime of w substitute t dt. So this will actually be helpful whenever we are solving problems under Ito calculus. So let's consider some examples. Example 1. If I ask to compute the Ito integral, so we are given this Ito integral and we are asked to evaluate it. So we can simply use stochastic integration by parts. We recall that integral limit from a to b f substitute t g prime of w substitute t, the wt from the formula is simply equals to f substitute t g of w substitute t ranging from a to b minus integral from a to b f prime substitute t g of w substitute t dt minus half integral from a to b f substitute t g prime prime of w substitute t dt. So this is the formula. Here now, we observe that our a will be 0, our b is t. What do we need again? Ft. Clearly, ft can be observed from here to be 1 because there is no function of time here. So that will be 1. And don't forget that we need this. This is once differentiable. So we need the first derivative. And the first derivative of this is simply 0 if you differentiate this. So, and clearly you can observe that g prime of wt now from here will simply be what? Wt. And from our formula, we need g of wt, which simply be the integral of this. And if you integrate this, just like we have integral of s ds is s squared over 2 plus the constant, but it's having limiting point, so it will just be that limiting point. And this will simply give us w squared, w substitute squared over 2. And we also need the second derivative, g prime prime of wt. So we are differentiating this one more time. And if you differentiate this, it will give us 1. Then that implies that integral from 0 to t, w substitute t, w substitute t. So let's substitute this to the formula. So f t now is 1, and g of w substitute t is given to be w squared substitute t over 2. So ranging from 0 to t minus, now you can see that this, the first derivative of f substitute t is 0, we make this particular term turns to 0. So we left with minus 1 over 2, integral from 0 to t. F is 1 and g prime prime is 1. So that will be 1 dt. And we can simplify further. So this one will simply, let's put in the limiting points. So this divided by 2 minus when it's at 0. And let's integrate this to simply give us t with the limit. Take note that in pronoun motion, one of the properties is that W of 0 is 0 from property of a Wiener process. So we'll be left with W substitute t squared. Then, if you put in the limit point here, I'll be having half t minus half times 0, which is 0. So this is simply the result of this Ito integral, as simple as that. Now let's consider another example. Example 2. Consider a Wiener integral equals to integral from 0 to t, c dw t, and 1 evaluate I substitute t. 2 find the mean and the variance of I substitute t. And there are some other problems you can consider, like the correlation and the covariance. But let's consider this first in this tutorial. So to evaluate IT, so given that I substitute t is integral from 0 to t, c dw t, here you observe that ft is simply dt, and since it is once differentiable, let's write the post derivative, but this is 1. And also observe that g prime of w substitute t here will simply be 1, where we can easily see our g of w substitute t to be integral of this, which is just w substitute t. And differentiating this, since it is well differentiable, one more time, will give us 0. And therefore that shows that our I substitute t, which is integral from 0 to t, t w substitute t, will be equals to ft of w t, which is t w substitute t reduced from 0 to t minus integral from 0 to t, the prime f prime of t, which is 1, then g of t, which is wt, then the t. We observe that the second derivative of g is 0. That makes the quadratic variation term to be 0. And putting our limit here now, we simply have capital T w substitute t minus 0, we should eliminate that one. Then integral from 0 t w substitute t dt. We know that Bernard motion is not differentiable, so it's not actually easy for us to compute the integral of this directly. So it's better we leave it this way. So let's move on to number figure 2. We have to compute the mean. And to compute the mean, we are performing expectation on the Ito integral, which is expectation on 0 to t, c dw t. From Ito integral property, this will actually simply give us 0, because the expectation is acting on the Brunel process. And we know that a Brunel process is normally distributed with mean 0 and variance t. So that implies that if we consider this, we can simply, since expectation is an operator, we can simply act on this. And from here, you can see that the expression of this one is 0. So simply, the mean is 0. Now let's obtain the variance. So the variance, that is var of I substitute t, will be var of the integral 0 to t, c dw t. So recall that var of a variable is always the expectation of the variable squared minus the mean of squared. Same approach here. So var of I sub t is simply expectation of I sub t squared minus the mean of squared. So putting the integral from 0 to t w t squared minus, but that our mean is 0 here already, so that will be minus 0. And taking the square of this, we have the expectation integral from 0 to t squared, wt sub t squared is dt. And taking the expectation of this will just be integral from 0 to t squared dt. And taking the integral, we are having t cubed over 3 to the limits, and that is going to give us t cubed over 3, which is the variance of the into integral.